In this video, we will be looking at the Henderson Hasselbach equation, its derivation, the limitations, and how it's applied to acid-base titration calculations, as well as buffers. The Henderson Hasselbach equation can be derived from the acid dissociation constant for a standard acid dissociation reaction. So if we take our standard reaction, which would be HA ionizes to form H plus plus A minus, the acid dissociation constant Ka is equal, it's an equilibrium, so it will be equal to the concentration of our products, so this will be H plus times A minus, divided by the concentration of our reactants. Now, the derivation for the Henderson-Hasselbach equation focuses on pH. So to get pH, we need to take the negative log of the H plus concentration. To do that, we need to get the H plus concentration by itself. So what we're going to do is we're going to take our H plus concentration here and solve for that value. So this would be our H plus is equal, and then you'd have your Ka. Then to move our HA and A minus to the other side, we're going to divide by the ratio, which would give us Ka times the concentration of HA over the concentration of A minus. Now, pH is the negative log of the H plus, so if we take the negative log of both sides, negative log of H plus is equal to the negative log of the quantity Ka times concentration of HA over concentration of A minus. Now, one of the rules of a log is if we take the log of two things being multiplied together, so the log of, let's say, A times B, that's equal to the log of A plus the log of B. So this would be equal to the negative log of Ka plus the negative log of the concentration of HA over the concentration of A minus, all wrapped in a set of parentheses. Negative log of H plus is our pH. Negative log of Ka is the pKa. And then we would have minus the log of the concentration of HA over the concentration of A minus. This is one form of the Henderson-Hasselbach equation. A more common one is if we use a different rule for logs, where the log of a ratio, A over B, is equal to the negative of the log of the ratio inverted, so B over A. If we apply that to what we have here, then we would have the pH is equal to the pKa minus the negative log, or plus the log, of the concentration of A minus over the concentration of the acidic form. This one here is the much more commonly used equation for the Henderson-Hasselbach equation. The Henderson-Hasselbach equation was developed or derived by Lawrence Henderson and Carl Hasselbach And the most common way that it is written is the way that we derived in the end, which is pH is equal to pKa plus the log of the conjugate base divided by the acid. Now, when we're using it in buffer solutions and most titrations, it's relying on the assumption that the H plus only comes from acid, right? Because we were using in our derivation the Ka for the acid, we were ignoring any autoionization for water. So because there's this assumption that the H plus only comes from the acid, that means that if we're working with really, really dilute solutions, it could be a problem. So some of the limitations of the Henderson Hasselbach equation are based on how it gets used. It doesn't really work for strong acids, and the reason it doesn't work for strong acids is because the Ka is so large that the acid completely disassociates, so you're not really establishing much of a dynamic equilibrium. Also, for moderately strong acids, those where the pKa value is bigger than about 1 times 10 to the negative fourth, some of the underlying assumptions of its use break down. It only works for moderate concentrations of an acid where the concentration is somewhere between 1 times 10 to the negative fourth molar to 1 molar. The reason for these limitations is at low concentrations, if we have a low Ka value, then you're starting to get into the realm where the dissociation constant for the autoionization of water starts to mean that the H plus concentration coming from water begins to matter. Now, the ratio of the acidic form to the basic form also has to be between a 10 to 1 and a 1 to 10 ratio. If you're outside of this range, then some of the underlying assumptions of how it gets used break down. Right, so the Henderson-Hasselbach equation is really only good when you have a pH that is essentially +1 or -1 pH unit from the pKa. In a titration curve, it's going to be good for the entire flat region of the curve. But during the curve bits, when you're approaching the equivalence point or at the very beginning of a titration curve, the Henderson-Hasselbach equation won't give you good results. Now, that midpoint, where the pH is equal to the pKa, that's the half equivalence point. And we can see why the pH is equal to the pKa at that location, because if we're doing a titration and we're halfway to the point where we've neutralized all of the acid, then half of the acid is going to be in the conjugate base form and half of it will be in the conjugate acid form. If these two values are equal, then what we essentially have when we plug it into the Henderson-Hasselbach equation is that the pH is equal to the pKa plus the log of the same number over itself, which would be 1. The log of 1 is 0. So under situations where the concentration of the conjugate base is equal to the acid, or that the base is equal to the conjugate acid, depending on what type of titration you're doing, where the two concentrations are equal, because we're taking the ratio in our equation up here, those concentrations cancel each other out, giving you the pH is equal to the pKa. So what this does for us is on our titration curve, if our curve looks something like this, the equivalence point is here. The half equivalence point occurs right here, and the pH at this location, at the half equivalence point, this is where your concentration of your base form is equal to the concentration of your acidic form, right? Because the equivalence point is when all of your acid has been converted into base, and there's essentially none of your acid left. So if you go halfway to that point, half of it's been converted. So at this exact location, your pH is equal to the pKa, right? And this is how we can actually figure out what the acid dissociation constant is from a weak acid, strong base titration.